Hello guys, this is Control Engineering. Now we are looking at chapter 3, which is in the time response of control system. Okay, so in chapter 3, basically we will be looking on the time response. We are looking into how control system react and basically exhibits their characteristics in time. We will also be looking at the Laplace transform. And after that, we have classification of dynamic system. After that, we'll be looking on this first order system, second order, and after that, we will see how the effectiveness of feedback system using controllers. All right. First of all, before as you all know, before we can design any control system, the actual prototype, we have to more or less develop the most accurate mathematical model about the system, about the control system. When we have this model in our hand, and we can basically predict the performance of the system long before it is being fabricated. So when we identify issue with the model, basically we can do a lot of changes, we can do modification to the model, and once the model is stable, then we can proceed to fabricating any control system. Okay, and how do we test the system performance? Basically, we can use a test signal, okay, such as a step response, ramp signal, and sinusoidal. Basically, if our system basically predicted to work in the environment that experience a lot of changes in the input, we can use a ramp signal as a test signal to test our system stability. But if our control system is working in the environment which works with the input that has sudden change, we may want to use step response, or maybe if our control system will be working in the environment with sudden change or sudden input changes, we maybe want to test our control system model with impulse response, for example. All right. Okay. Of course, simple control system mathematical model can be represented by a transfer function. You have seen in lecture 2, we are talking about transfer function using ordinary differential equation, and we have touched a little bit on the Laplace transform and how to do some simple solution. All right, from here onward, we will be working a lot with Laplace transform. So you have seen the Laplace table transformation from lecture 2. All right. So Laplace transform is basically some kind of mathematical framework that actually help us to do to find solution for uh, ordinary differential equation. So for example, in this control system, we may be working with complex mathematical equation, long mathematical equation with differential equation and all that. So Laplace basically can help us simplify those things, which basically transform from the time domain to the S domain. We can do futuristic solution from there. We can do many things from there. in the S domain, in the Laplace domain, and of course, we can always go back to the time domain later on. For example, here in this slide, we see given a function f of t, any time domain function, any ordinary differential equation domain function, defined for values of variable t is bigger than 0, then the Laplace transform of f of t is denoted by this capital L, curly braces f of t. Okay, the exact or the correct definition of Laplace transformation is improper integral between 0 to infinity exponential minus st. So this is where the s came from actually, and our function f of t dt. All right, so this is the actual definition of Laplace transform. For example, here, if we were working on the function f of t is equal to 2, and what we will do basically is that we will replace f of t as 2 in the equation, and basically we will finally have Laplace transform of constant 2 function f of t equal to constant number of 2 is that constant number multiplied by 1 over s. So basically you will have finally 2 over s. All right, and of course you can do forward transformation, and you can always do backward transformation using inverse Laplace transform. For example, in this case, for over s, once you do the inverse Laplace, you will have the time domain signal again. All right. Okay. Again, most of this transformation from the time domain to the Laplace domain, you can find many of these things, but to make our computation or our work, a little bit faster, you can find this very common transformation in the table, so you can basically use it anytime you need to use it, basically. So this is example of how do you do Laplace transform of derivatives. All right, not only you can transform function in terms of constant number, but you can also transform derivatives. All right, in this case, and for example, here you have ft is in the form of derivation. So basically, you put in the ft here in the Laplace transformation equation, and you can take out this one. All right, and you have s, and then integration of the function of f of t, and then basically when you do this limits thing, you will get finally something like this. So integration of any function of Laplace transformation of any derivative function, you will have in the Laplace domain, you will have this kind of term basically s f of s minus f of 0. Okay. This is two properties of Laplace transform. They say here the first one, sum or difference. You can straight away do the sum and difference. The same here for the case of multiplication. All right, you can straight away do it. The next, and this slide, you will see basically how do we solve differential equation using Laplace transform. For example, here you have f of derivative f of t plus f of t equal to 1, where f naught, f0 is f naught is equal to 0. So we take Laplace transform for both sides. Basically, we have Laplace transform of the 1, Laplace transform of a derivative function, and Laplace transform of a simple function, and equal to this one. And of course, Laplace transform of any derivative function, you can straight away take the term, as you can see from the previous slide, this one. Then Laplace transform of the function of t here, you can straight away replace this one. And then Laplace transform of a constant, you will have this term. And finally, you will have f of s is basically the whole function. We will be taking this form. All right, this is very easy to see. But this is very much how you solve differential equation using Laplace transform. Okay. And of course, from the Laplace, from the equation in the Laplace domain, basically you can revert this thing back to the time domain following this steps, which you have to know how to the partial fraction expansion, and then you can use the inverse Laplace information from the table to get this thing back. All right, this is going forward from the time domain to the Laplace domain, and inverse going backward from Laplace domain to the time domain. All right. Okay, we have a couple of examples. You can basically take a look yourself how Laplace transform is being done, from the time domain to the frequency, to the Laplace domain using the information from the table. So this is linearity. This is basically the properties of Laplace transform. You can see many other examples on how to transfer from the time domain to the Laplace domain using the information that you can get from the table. Okay, so also you also have to know how to work with Laplace transform using step function, using ramp function, using Hall function, and of course sinusoidal function. Because all of these functions basically they have the Laplace what they call that transformation, and of course because in this particular topic we want to basically test any control system with a test signal. We want to predict the characteristic or the performance of any control system using the test signal. So the control system transfer function, you have to work with the disturbance function, for example, unit step, ramp, impulse, and sinusoidal, because this is the test signal that you are going to induce to your control system transfer function, that you know at the end of the day whether your control system or your mathematical model that you are developing is stable or unstable. Okay. So basically, how do we classify dynamic system, such as control system? You may have seen this in the lecture 2, in which you can basically do this kind of classification by looking at the transfer function of any control system. For example, here we have the order, which means the highest power of S at the denominator, the class, the type, the rank, and everything. So basically, you can use this information to classify any dynamic system. Okay. The first order and the second order system are going to be explained in the next lecture. Thank you.